All right, welcome to our first pre-lab video. This is pre-lab for virtual lab number one being the heat transfer between objects lab, which is for Thursday, January 21st, 2021. Now, in this experiment, what we are looking at is a pair of really fundamental concepts that exist in the world of chemistry and physics. And those are the concepts of heat and temperature. Now, you may recall from our definitions in Gen Chem 1, temperature is the measure of the internal kinetic energy of a substance, whereas heat is the energy associated with changes in temperature for an object. So that is the difference between the two. Temperature is the measure of the internal kinetic energy. And so when an object increases in temperature, its internal kinetic energy also increases. And when when it is cooled, when its temperature goes down, the internal kinetic energy of that substance goes down as well. Heat is the energy that is associated with those temperature changes. So when a temperature decreases, we see that it is losing heat energy. When something absorbs heat, heat is said to increase the temperature of the object. So the two are different from each other, but in a lot of ways they appear to be kind of the same. So the other aspect of this particular lab that we are going to investigate is a pair of concepts known as heat capacity. That is the amount of heat required to increase the temperature of a substance by 1 degree Celsius, and its very close cousin, specific heat, which is the amount of heat required to increase the temperature of 1 gram of a substance by 1 degree Celsius. So the two objects here, the two measurements of heat capacity, of heat, specific heat, are very close to each other as well. We tend to favor this second definition more because it gives us an even playing field, an even ground. I can compare the specific heat of two objects directly because I know that I'm heating the same amount of each substance. Whereas a 50-pound block of iron and a 2-gram sample of water are going to require drastically different amounts of heat to increase their temperature, but they're not going to be the same thing at all in terms of, having a real good comparison of the two against each other. So we tend to favor specific heat for that reason. And there's a relationship between specific heat of a substance and the amount of energy that is generated by that heat transfer. And the equation that we use there is Q is equal to M times C times delta T, where Q is the heat transferred in the process, It can be positive or negative. Positive means that heat is absorbed by the substance. Negative means that heat is released by the substance. So that's Q. M is the mass of the substance itself. So here's where we account for different amounts of substances. C is the specific heat of the substance, and its unit is joules per gram per degree Celsius. And then dT, delta T, is the change in temperature for the substance. And that is in degrees Celsius. So this last term, dT, I've kind of given it in terms of its kind of integrated calculus form. The other form that you'll tend to see with it is the Greek letter delta T. So these two are interchangeable from that standpoint. But this is the equation that you would use for determining how much heat has been transferred into a substance or out of a substance as its temperature is changing. Q is equal to M times C times delta T. So in looking at the pre-lab assignment for this particular experiment, what we're going to see is that for the most part, most of the questions here are along the lines of conceptual kinds of questions. Do you know the difference between heat and temperature? Can you use that definition to explain why a thermometer works the way that it does? Or why alcohol is used instead of water in modern thermometers? This last question is a question that is specifically for that specific heat kind of question that we are using. So what we're going to do now is you should be able to answer questions 1, 2, and 3 kind of already. If you can't kind of figure your way through those, a relatively simple search online should help you to kind of figure out how to answer those 3. For question number 4, though, let's go back to the whiteboard and do an example. Determine the heat transfer when 31.9 grams of water is heated from 11.9 degrees Celsius to 31.1 degrees Celsius. For this question, you are going to need to use that equation. Q is equal to M C delta T. In this case, our value of C, since we are dealing with water, is 4.184 joules per gram degree Celsius. So every single substance has its own specific heat value. The specific heat values that are relevant to, well, pretty much any problem that we can find, we usually can find those in a reference text of some sort, or in our cases, your textbook. In our textbook, the Values are found in Chapter 10, specifically Table 10.3 on page 459. And so you can see in this table there are lots of different specific heat values. You can see that specific heat values in that table are have a lot of different variation, and actually water itself has a number of different specific heat values depending upon what phase it is in. So for liquid water, which would be the state of matter that it is in for this range of temperatures, that is our value. And so all we would need to do is to figure out the values of M and C and delta T. For delta T, remember that delta anything is just the change of value for it. So the value of delta T is equal to the final temperature minus the initial temperature. So in this case, our final temperature is 31.1 degrees C. Our initial temperature was 11.9 degrees C. So our delta T in this particular case is, get my calculator out, it would be 19.2 degrees Celsius. So 19.2 degrees Celsius is our value for dT. So now putting it all together, Q is equal to the mass, 31.9 grams, multiplied by the specific heat, 4.184 joules per gram degrees Celsius, multiplied by the specific heat, or excuse me, the change in temperature, 19.2 degrees C. If I put all of those in a line together, you can see that my grams cancel out, my degrees Celsius cancels out. All that is left is the value of Q. Q is equal to 31.9 times 4.184 times 19.2 and to three significant figures, I get 2,560 joules of energy. Sig fig issues are important in these kinds of calculations because often we have a lot of estimation in our temperatures. So we want to make sure that we do not overestimate or over analyze our value for delta T or for the heat that is transferred as a result. Note also that this is a positive value, positive 2,560 joules, and that is because heat is entering the water. That energy is causing the water to increase in temperature. If this value were negative, if our delta T value were negative, that would be because heat is leaving the water because it is dropping in temperature. So that is how to go about doing the problems like the ones in the pre-lab. So hopefully this is a good introduction to thermochemistry for you. If not, feel free to leave me a comment or send me a message on Remind or an email, and I'll be happy to answer your questions regarding this concept overall, or specifically the pre-lab that you are being asked to do. But until that time, have a good day. I will see you on Thursday.